Hi, welcome to the second part of our discussion for geometric transformations. We've already done reflections in the previous video, so now we're going to continue our discussion for the other types of linear transformations. The first one that we have is rotations. Rotation is a transformation that turns all points in an image around a fixed center of rotation by a specified angle and direction. So, a rotation transformation is a linear transformation if and only if the center of the rotation is the origin. Any rotation transformation preserves the size and the general shape of an image. However, it changes the radial orientation of the image. So, this is what a rotation transformation would look like because the center of rotation must always be at the origin. So let's have some few examples that we have for rotation transformation. The first one that we have are mandalas. So mandalas have circular patterns that highlights rotational symmetry. One easy way of generating them, especially using digital media, you can use apps for this, is to generate one slice of the mandala and then subjecting the slice to consecutive rotations about a center of the piece. So, for example, you only need to create a unique pattern for one slice. And then after finishing that, you just copy it to the rest of the circle to make a mandala. Next, that we have another interesting example from nature is the heliotropism of sunflowers. It is the rotation of sunflowers to follow the sun from sunrise to sunset. The rotation is controlled by sunflower circadian rhythm and their reaction to sunlight. So this is what it looks like. Let's wait for it to load. So as
Playing
you
from
can see
downloads.
here, okay, so this is what it looks like. So it follows the sun from sunrise to sunset. So it rotates on a fixed point here. Next, so these are the examples of rotation transformation in nature. Now let's go through what it looks like in a Cartesian plane. So for example, we have triangles with vertices A, B, and C, and we perform a rotation transformation with the origin as the center of rotation as at an angle of 90 degrees clockwise. So from ABC, we rotate it 90 degrees clockwise to get XYZ. So from all of these coefficients or all of these points, we get this. Okay. So that's what rotation transformation would look like in a Cartesian plane. Now, aside from that, let's have another example. So if we rotate it at a 135 degrees counterclockwise, these are going to be the points that we have. So we've done XYZ already, right? So 90 degrees clockwise. And then if we do 135 degrees counterclockwise, these are the results. So if you simplify this, this is just -7 square root of 2 over 2 and square root of 2 over 2. So those are the components. Okay. So how are we going to get this if we have to directly or accurately solve for the components? So one thing that we can use is this formula. Okay. So it says that the rotation of point AB in r squared with the center of rotation at the origin and angle of rotation theta counterclockwise is a linear transformation given by this formula. So we have cosine theta and sine theta for this. So I already did the computation for the 135 degrees counterclockwise. So theta is going to be 135, as you can see here. And then from here, all I need to do is to solve for cosine 135 degrees and sine 135 degrees, plug it in here, and this is our formula. So this is what we're going to use to solve for all 3 points. So our original point that we have is ABC. And then from here, oh, wait a sec. So we have, okay. Okay. So these are the values that we're going to have. So if we for example plug in the values, so this is the formula that we have. So if we plug in the values, okay, let's have this as an example for 2, -2. So A is equal to 2, B is equal to -2. So let's solve for the x component. Okay. So x component is -a. So -2 times square root of 2 over 2. And then minus b component is -2. So that's -2 times square root of 2 over 2. And then we get 0. Okay. That's how we solve for the components. And then for the y component, we have b. So -b, we start there. So that's negative b. B is -2. And then this is plus now. And then -b square root of 2 over 2 plus a. So plus 2 square root of 2 over 2. So we get 2 square root of 2 here. Okay? So that's how we solve for the components. So please also try it here and with also with our first point. So if you look at the original values that we have here, then it's the same. So that's how you solve for it. Okay? Next, what if you are tasked to find XYZ? So XYZ has a 90-degree rotation, but it's clockwise. So how are we going to use the same set of formulas if the rotation is clockwise? So this is what it looks like, right? So these are the values that we have. So notice that I have already drawn it here. 90 degrees clockwise will end up here on the positive y-axis. So that's the same thing as saying that we rotate 270 degrees counterclockwise to end up at the same place. So if theta or your given rotation is clockwise, all you need to do is to subtract it to 360 to get the counterclockwise motion. And then if it's given in radians, you use 2 pi instead. So using those values, again, our theta now is 270. So if you solve cos sine 270 is 0, sine 270 is 1. So if you plug in the values here, this is going to be a times 0. So that cancels out. Minus b times 1, right? Because this is 1. So that's 0 minus 1. 0 minus b. Okay. Oh, so 0 minus. So let's solve for sine 270. Oh, sine 270 is equal to -1. So we have -1. So that's negative b times -1. So that's equal to negative 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 b times negative 1 is equal to positive b. Okay? And then from there, you can also simplify yung y component. And then from here, you can solve for the points. Okay? So I'm going to show you how to solve for the second component first here, just to clarify or to show you that it's going to be a. So let's plug in the values. B cosine theta plus a sine theta. So b times 0 plus a times negative 1. So this is going to be 0 plus, or this is going to be negative a. So that's negative a. So that's why we got negative a here. And then from there, we can use this to solve for all the points. So let's see if we are going to get the same values as this. So let's solve. Again, this is A, this is B. So let's use our calculate. Oh, we don't need to, because this is the things that we're gonna do lang. So switch. So B will be our X component, and then the Y component will be negative A. So negative 0 is still 0. So it's the same. Again, switch 3, 4, and then the Y component will be negated. And then lastly, let's have switch again, negative 2, 2, and then you have to switch the sign. So let's see. Yes, it is the same. Okay. So that's how you solve rotation problems, knowing that the center of rotation is at the origin and the angle of rotation is given clockwise, in a clockwise direction. So if you need more examples, you may refer to your book. But yeah, that's the gist that we have. Now, for our second type of linear transformation here in this video, we have dilation. So the dilation refers to the transformation that scales all points in an image around a fixed point called the center of dilation by a specific constant factor. In other words, a dilation enlarges or shrinks an image but preserves the general shape or proportionalities of the image. Okay? So our a dilation will be a linear transformation if the center of dilation is at the origin, just like what we have before. Okay. So these are the examples that we have. So we have a dilation. The original picture is here, and then we enlarged it. So proportions are still the same. We can also shrink it, and then we can also have a combination of different linear transformations. So after enlarging, you can reflect it. So examples that we have of dilation, of course, we have the pupils. So it enlarges or dilates based on the brightness that we have, that we receive. Now, knowing that the dilation also preserves the shape and proportionalities, this is what it looks like if we enlarge an image with respect to the origin. Okay. So, with this in mind, let's have the different factors that we have when we are enlarging or dilating. So, this is the formula that we're going to use. We just need a scale factor. You will be given a scale factor k, and then you just need to multiply that the components. Okay. So again, we can only use this if the center of dilation is at the origin, and then we have a non-zero scale factor. So that's what we're going to do. Okay. Now, even without solving the values yet, you should already have an idea on what the image would look like based on the scale factor. So let's maybe we can put it in a in a number line. Maybe that will help us. Again, we are not allowed to have zero, okay, as a scale factor. And then if the scale factor is greater than one, we know that, oh, maybe we can change the color. If the scale factor is greater than one, we know that the image will be enlarged. Okay. And then if it's between 0 to 1, then that just means that the image will shrink. Maybe we can put it here. Shrink. Okay. If it's 1 exactly, no change. Okay. And then if it's between -1 to 0, then the image will shrink and be reflected about the origin. So let's have it here. -1. Oh, shrink cross reflected about the origin. And then -1, that means it's just reflected. And then lastly, if it's greater than -1, maybe let's use purple. Then the image will be enlarged plus reflected. So those are the meanings of the different scale factors that we have. Okay. So again, this applies for the coordinates. Okay. So now let's have some examples. So for example, we have a rectangle with these vertices, and then we have to multiply it by a scale factor of 2. So that means scale factor of 2, we are enlarging the rectangle. So from, maybe we can, okay, let's use a Cartesian plane. So let's draw our original triangle. So our original rectangle, we have 1, 2. So 1, 2, 1, -2, -1, -2, and -1, 2. So this is our original rectangle, and then we are going to enlarge it with a factor of 2. So if we do that, we are going to just multiply it by 2. So this is going to be 2, 4, 2, -4, -2, -2, 4, -2, -4. So this are the points that we have now. So let's plot, let's put a name for each point here. So A, B, C, and then D. So let's plot the new points 2, 4. So this new A, and then 2, -4, new B, -2, 4, new C. And then we have new D. Okay, and then after that, yeah, that's what it looks like when we enlarge it with the scale factor of 2. Now, what if we uh, we enlarge it with a scale factor of -2? Now, if k is equal to -2, so aside from it being enlarged, it should be reflected with respect to the origin. So the new points that we're going to have, we have -2, -4, -2, +4, negative 2, -4, and then we have 2, 4. So these are the new points that we're going to have. So let's plot it. -2, -4 is here. -2, -4. So this is where A will be placed in. And then 2, -4 to -4 is where, sorry, -2, 4. So this is where we'll find B. And then 2, -4 is where we'll find C. So let's put 2. Okay. And then lastly, we have 2, 4 for the double prime. So we essentially have the same rectangle, right? But it is reflected with respect to the origin. That means here, okay, so aside from, wait, our original point is A here, it gets transferred. As when we say reflected with respect to the origin, aside from flipping, this is the original A prime, right? And then we want to go here. So that means you are reflecting it first on the x axis, about the x axis, and then after that, you reflect it about the y-axis. So that's what it meant by reflecting about the origin. So you can search for it on the internet if you want more examples. But yeah, that's essentially what it means. Okay. We also have some examples in the book for dilation. So here we have a scale factor of -1/2, and this is what it looks like. Okay. So the points, maybe to visualize it better, you can plot it with a scale factor of 1/2 first, and then from there you can check, or you can also plot the -1/2 scale factor to really see the difference. Okay. And then if we have, for our next example, if we have um equations or functions, this is how we're going to solve for the scale factors. So for the scale factors of functions, all we need to do, so for example, we have this parabola. So we have a scale factor of 4 first. So let's have k is equal to 4. So it is the same as the concept that we have in the definition. So x and y will be scaled with a factor of 4. So y equals x squared plus 1 will become, y will become 4y, x will become 4x, and then it will become squared plus 1. We can simplify 4y is equal to 4 squared is 16, x squared is x squared plus 1. And then from there, we can solve for y because our equations usually just have y equals something, right? Our functions. So 16 divided by 4, that's 4x squared plus 1 fourth. So this is now the equation when we have a scale factor of 4 and then a scale factor of, let's say, maybe let's have negative 1 half just to show you how it works. So if it's negative 1 half, we'll do the same thing. So y is equal to x squared plus 1. This will become negative 1 half y plus negative 1 half x squared plus 1. Simplify, this is just negative y over 2. If we square negative 1 half, that's just positive 1 fourth. And then we have x squared plus 1. So to get rid of, let's just rewrite everything. So I want to remove this parenthesis. So 1 times x squared is x squared over 4 plus 1. And then we want to isolate y. So we are going to multiply negative 2 on both sides. So that this is just y na lang. And then we have negative 2 divided by 4. That's negative 1 half. So negative x squared over 2 plus, oh, sorry, minus 2. So that's what it looks like. Okay. So that's what we mean when we have a um, scale factor of negative 1 half. And then from there, we can uh, plot the graph, or you can use a graphing calculator to see what it looks like. So I have pre-made some. So this is the original one, original. And then this one is with a scale factor of, what was it? 2? Oh, 4. Okay. And then this one, scale factor of 1 half. Okay. So if you have to plot it with negative 1 half, this green one will be uh will be reflected only. Okay. What I reflected actually is the 4, scale factor of 4. So you may also try to solve it yourself. So this is k equals 4, and then this is k equals negative 4. So you can see that they are just reflected about the origin. Okay. So that's how we solve for dilations. Okay. So if you have any questions, just put it in the comments, message me. But yeah, that's our discussion on the last two types of linear transformation.